Let's continue with temporal coding. To make the code more efficient, it removes the temporal correlation between signals so that the coding output looks much less correlated in time to carry less redundant information. Let's expand the input signal, look a bit more in detail. We see that the signals at nearby time instances are very correlated. But this correlation is much less so at the output. And this is achieved by this temporal filter for the efficient coding. It looks like this. It integrates input signals within a time window of about 0.1 second. But it takes the difference between time inputs that are spaced about 1 second apart from each other, so that previous input signals about 0.1 seconds before the current one contributes an inhibition to the current response. So this is how it integrates in time, it contributing an inhibition. This way, correlations between two time points of this time difference can be removed. Yeah, and this filter is achieved by having such a gain function g omega as a function of frequency omega, and this g function is gain function comes from this efficient coding. In particular, note that this gain function peaks around 5 to 10 hertz frequency, and this corresponds to this around 0.1, 0.2 seconds of time scale in this temporal filter. Let's apply the temporal filter to this input example. The input signal onsets at time 0, stays on, and then offsets at time t equal to 1 second. At time 0, this filter immediately sees the change in signal from 0 to 1, so it gives an output, positive output pulse through this integration, while any inhibition from the recent past is 0 because the recent past input is 0. So the positive increase is reflected in this positive pulse in the response. However, during this time window, there's no signal change. So therefore, the integration of any ongoing signal is cancelled by the inhibition of the signals in the recent past. They're exactly the same. So inhibition and excitation cancel each other. That means at the output, there is no response. This means any continuing signal that is similar to the recent past signal is predicted and then ignored. Then when the signal suddenly drops, this drop is not predicted, so the output response goes negative. Therefore, you can see that this filter is more sensitive to temporal changes, sudden increase, sudden decrease, but is insensitive to temporary predicted signals. And these kind of coding transform from this to that is called predictive coding. We can compare this more artificial signal to this more natural-looking signal. In either case, the predictable part of the signals are more or less ignored, while the output response is more sensitive to input signal changes. For example, this peak perhaps corresponds to the response to the sudden rise here, and this dip perhaps corresponds to this sudden drop here. Yeah. And the time scale in this integration window or in this filter should be similar to the time duration of each of these output pulses. This predictive coding filter removes the redundancy so that the output is less redundant and the responses are more transient. However, as we know, redundancy reduction is more suitable when the input signal to noise is high enough. Yeah. However, if you are in a dimmer environment, the input signal noise may be too low, and then the filter will adapt by such efficient coding. Yeah. Now, given that the signal power is having such a power spectrum where it drops with frequency omega, the peak of this gain function will also shift towards lower frequencies, so that the whitening region in which the gain increases with frequency will be at the lower frequency region where the signal is still high enough over noise. And if you do like this kind of adaptation, the filter will be more lower pass rather than a band pass. And correspondingly, this filter will also become fatter, integrate more in time to smooth out noise and integrating signal. And also this inhibition region will get weaker. And so it will more like an integration filter. And then the output will be less transient, but more sustained. So it will be sustained, more sustained input. So if you have an input onset and go on, it will not drop quickly. It will just integrate and do a more sustained response. And then the output will be no longer as sensitive to sudden input tempo changes. And when the perception does pick up input changes, the response latency will also be lower because it needs to integrate for a long time before it can be sure that something has happened.